We will now go ahead and work with the third example. In the third example, suppose that the true probability of any randomly selected person voting for Jones, suppose it was only 10%. Then what would be the value of the beta, right? So remember, beta is continue to accept the null hypothesis while in fact the alternative hypothesis is true. So you guys can imagine, so what I did is I copy pasted our progress so far about the alpha calculation. Alpha will not change. The beta calculation now will change. So this was our solution to the second problem. So what I will do here is to just update the numbers. So if the true probability of Jones winning is only 10%, then it's very likely that y will be either 0 or 1 or 2, and then 3 or higher is even less likely, right? So if Jones is the probability that any randomly selected voter will vote for Jones, if this was only 10% in reality, what is the likelihood that if you randomly select 15 people, 10 of them will vote for Jones? Extremely unlikely. I mean, almost zero probability. So then the question is, the beta is, because our rejection region is y less than or equal to 2, for the beta we will need to find y greater than 2, right? So the probability of committing a type 2 error, right, would be basically continue to accept the null hypothesis while in fact the alternative is true. So what we will do is, like we said, so we're going to change this probability to 0.1, and all of them we changed it. Now the answer would be, well, the probability that we will end up in a rejection region is here. So as a result, the beta has dropped suddenly to 0.184. Now, that's still a pretty large number, even though it's extremely unlikely that Jones will be selected. Obviously, the true probability is only 10%. He will only get 10% of the votes. And yet, look at this beta. We have almost a 20% chance of committing a type 2 error. Like the polls ahead of the election, they have a 20% chance of making a mistake and continue to believe that Jones will be the winner. So this is a big problem. So what is the lesson that we learned from this? Like I said in the previous video, there's a trade-off between the alpha and the beta. So the size of the rejection region is very important. So by picking the rejection region as these last two, like 2 or less, we are making it very restrictive in order to make sure we are not committing a type 1 error, namely to reject the null hypothesis while in fact, to reach a type 1 error in the sense that we continue to reject we reject the null hypothesis while in fact it is true, right? We certainly don't want to commit such an error, right? So in order to not commit such an error, a type 1 error, I should say, of rejecting the null hypothesis while in fact it is true, what we do is we are very restrictive in our choice for the rejection region, but then suddenly look at the beta. The beta is totally unacceptable. So what we need to do in this example is to expand the rejection region. We realize that a rejection region where y is less than or equal to 2 is not going to work for us, right? So what we want is a better rejection region, and that's why I will go to our next to my handout here. So let me just go ahead and describe the situation here. Let's work on this. So the question then is the following. That's exactly the next example. Now we are going to make a small modification. Actually, let me just at the same time try to move that window. I don't know if it's gonna let me while I'm recording. Let's hope it will. Actually, it did a little bit. Okay, good. All right, so Well, we have this new rejection region, all right, where y less than or equal to 5, and we want to calculate the level of alpha of the test, the level alpha of the test, and calculate the new beta. Calculate the beta if p was 0.3. Back to the example 2 situation. Compare the results with the values obtained in examples 1 and 2. So compare it with the situation for when we got alpha and beta if the rejection region was 2, right? Y less than or equal to 2. Let me first go ahead and mention these, right? So we got when the rejection, let me write that down, when the rejection region was such that y is less than or equal to 2, then then I think we calculated alpha to be extremely small. Like the probability of committing a type 1 error is extremely small, but this comes at the expense of committing a huge type 2 error. And we were not happy with that. So instead, now we are proposing a bigger rejection region if the rejection region were to be, oh, sorry for that. There's a 2 here. Now, what if the rejection region wasn't y less than or equal to 2, but what if it was y less than or equal to 5? So that's what the question wants us to try. Let me move it up. Then we want to recalculate alpha, recalculate beta, and it is very straightforward. So basically, we just follow the same steps. Alpha is again the probability that y is less than or equal to 5 if p were to be 0.5. How likely were we to, if p equals 0.5 were true, how likely do we to observe this probability to be less than or equal to 5? Let me actually have 2 steps here. So we basically plug it to the binomial distribution again. So we start with 15. Well, obviously you guys will use Excel. 15 choose 0, 0.5 to the power 0, 0.5 to the power 15, plus ... But so what we will do is, we'll go all the way up to 15 choose 5, not 15 choose 2. We'll go all the way up to 15 choose 5, 0.5 raised to the power 5 times 0.5 raised to the power 10. If you were to add up all these quantities, and it's very easy to do it on Excel, you would have gotten 0.151. Now compare this also with and then let's first have the beta as well. By the same token, the probability of committing a type 2 error, meaning y is strictly greater than 5 when p is when the true probability is 0.3, say, right? This thing again, so what we will do is, starting with 15 choose 6, y is greater than 5, right? 0.3 to the power 6, 0.7 to the power 15 minus 6 is 9. Go all the way up to 15 choose 15, basically 0.3 to the power 15, 0.7 to the power 0, I say. And indeed, if you calculate this comes out as 0.278. Now, this is, I think this is a more reasonable outcome, right? So this is like a compromise solution. 27.8, I should say here. 27.8. So the probability of committing a type 1 error, alpha, is 15%, and the probability of committing a type 2 error, or beta, is 27.8%. And this seems to be a compromise answer. Now, you might say, wait a second, these are not satisfactory at all. I want to be much more confident than making a 15% error. Well, the only way you can be more confident is by having a larger sample size. Just asking to 15 people won't give you the result that you need, right? You need a significantly larger polling sampling size, and then you will have a much better confidence. The level of the test will be much better, and the probability of making a type 2 error also will be much better. So that's why, for instance, political polling, like surveys, they ask usually at least to about 1,000 people, usually 3, 4, 5,000 people. When you ask it to so many people, these probabilities will fall significantly. Committing type 1 error and type 2 error will be significantly lower. Now what I want to do is, before I conclude this video, let me also show how to do this on Excel. Let's hope we can find it. So this is example 4. So we did the example 3 earlier. So for example 4, like we said, you know what? I'm kind of lazy actually. Instead of redoing the whole thing, why don't we just go to the previous things that we did? So we calculated alpha previously. So what I will do is, because the new rejection region is y is less than or equal to 5, or maybe I can do the following. I can just copy paste. Okay, so yeah, that makes more sense. Let me not ruin what I did so far. Control V. Okay, perfect. So what I will do is, because we want y to be less than or equal to 5. And I think we calculate in 2 ways. We don't need that. So all we do is we need to sum F2. Instead of summing y equals 0, 1, 2, we need to sum all the way, right? So sum from 0 all the way to 5. That's our new rejection region. And yes, so alpha, so this number turns out to be the alpha, is indeed 15.1%, just like we manually mentioned it earlier. And for the beta, well, actually, I need to go to that page where we did the beta calculation. Again, select all of it. There you go. Control C. And let's do the calculation right here. Control V. So here, the 0.3 will remain. Instead, yeah, like previously, we want the less than or equal to 5, right? Again, we don't want to do it in 2 different ways. I'm just going to remove all this. All right, one way is sufficient. So F2, oops, I keep pressing the wrong button. Function F2. All right, so less than or equal to 5, right? So there you go. And now 1 minus that, suddenly this number changes and it becomes 27.8, just like we did when we solved the question manually as well. So Excel is pretty much how you should be doing it. But when you write your solutions, you can write it on a piece of paper after you did the analysis here. So going back to this, so the lesson that we learned from all this is we can change the rejection region. So we analyzed the rejection region for 2 different situations. If the rejection region were less than or equal to 2, y is less than or equal to 2, then alpha is extremely nice. The probability of making a type 1 error is extremely small, but it comes at the expense of almost surely making a type 2 error. Now, by expanding the rejection region, we find a compromise solution where alpha is now, we sacrifice some alpha. Now we are significantly more likely to make a type 1 error, but the type 2 error is down. Some of you will say, hey, this is not acceptable either. So you can keep changing the rejection region, but you can only do so much by changing the rejection region because the sample size is extremely small. So n equals 15 is way too small to come up with some good estimates and making small errors, type 1 or type 2 errors. So the only way out of this thing is if you increased n to, instead of 15, for instance, if you were to increase it to 100, then you will start getting some really, really nice results, right? So what I will do is, before I conclude this video, so let me actually give you a sample of that. So let me just go ahead and go back to the Excel. So let's recalculate. Actually, let's do it over here, I guess. So this was our example 4. Let me not ruin this page. So let me just extension. So we are going to extend the results with n is equal to 100. What if the sample size was 100? So what I'm going to do is I'm randomly asking 100 people about their opinion, and let's recalculate alpha. Let's assume that the true probability of any individual voting for our candidate Jones is 30% only. Obviously, alpha will be independent of that because the null hypothesis is that it is 50%, right? So let's just go ahead and calculate these probabilities again. I'm just going to I'll be lazy as usual, just copy paste this whole thing. There we go, Control C. And so this way we are able to Control V. All right, so the sum won't be here anymore, obviously. and obviously these numbers should start all the way from 0, 15, actual all the way to 100. You poll 100 people, you ask them if they would vote for Mr. Jones. Well, the likelihood that all of them will say they will vote for Mr. Jones is obviously extremely unlikely, right? So, but this is a hypothetical thing. So the sample size is 100 now, and perfect. So I'm going to double click here and then double click here further. Okay, good. Oops. So if you ask 100 people, and if indeed Mr. Jones had a 50% chance of a randomly picked person has a 50% chance of being a supporter of Mr. Jones, what are the likelihood that when you ask to 100 people, none of them will say they vote for Mr. Jones? No chance. 2 people, even 10 people is no chance. 20 people is still no chance. The first chances start appearing if at least 26 people say they will vote. But in general, the most likely event is 50%. Like 50 people saying they will vote. I mean, about 7 or 8% of the sample will say that they will be voting for Mr. Jones. All right, this is the most likely thing. Half of the people, 50 of the people, of those 100 people sampled, will say they will be voting for Mr. Jones and so on. So here, what we can do is we can change our rejection region. So instead of what I can do is I can pick a rejection region. How about we pick a rejection region where earlier we used to pick 2 first, then 5 when the sample size was 15. Now the sample size is about 6 times as big. Why don't we make exactly 6 times actually? That's a way better thing. Okay, let me change it one more time. 90 is good. So let's change this one F2 to 90 here. I think this will be a way better. So I'm just increasing the sample size by 90. All right, there you go. Obviously after 90 it won't make any sense. That's why I need to cancel it here. And here I will choose the 2 different type of rejection regions. The first experiment that I want to do is a rejection region where 6 times 2 is 12. How about 12 here? What will be the alpha if it was 12? So F2, we want to sum all the things up to 12. The sum of all these numbers. Obviously it will be either 0 or extremely close to 0. Alpha is extremely nice. There's no chance we will commit a type 1 error, right? Let me write that down. Probability of type 1 error is 0. Very good. And let's do the same thing on this side. I will be lazy, I guess. Control C. Whoops. Okay, just paste it here. Oops. All right, and here we are changing the 0.5 with 0.3 because that's the true probability of the vote for Mr. Jones. Okay, there you go. So first let's calculate less than or equal to 12, and then we will subtract it from 1. So therefore, I want to add all these numbers less than or equal to 12, and as a result, you know what? I'm just gonna copy these things here. As you can see, beta didn't come out nicely. There's a 100% chance we will make a type 2 error. Probability of type 2 error. Probability of type 2 error is 100%. Horrible. Here, probability of type 1 error is 0%. So 0% is amazing, smiley face, but 100% is horrible. So this is a sad face. Oops, a sad face. So what we can do is we can change our rejection region. How about we change it to y? Let's see if we can find a compromise solution, right? Y less than or equal to, looking at these numbers, I think I'm going to choose, how about 25? Less than or equal to 25. Okay, so let's see what will happen here. As usual, we will just add up the 25 numbers, equals the sum of the first 25 numbers. There you go. Press enter. Now there's a tiny bit. Actually, let me just represent this as a percent. I mean, even after I add decimal place, it's still 0%. Alpha, the probability of making a type oh shoot, hold on, a type 1 error is still 0%. I'll do it gradually, don't worry. Actually, hold on, Control X. Okay, and how about the other side? The probability of y being less than or equal to 25 if the true probability was 0.3, right? So we just need the equal to the sum of those 24 numbers, oops, 25 numbers, I should say. Press enter. And as a result, the probability that y will be strictly greater than 25 is just equal to 1 minus that number. Wait a second. All right, so this is a percentage, and maybe I can add 2 decimal places. Okay, so this is the beta, the probability of making, oops, oh shoot, I did the same thing, beta. All right, the probability of making a type 2 error now is 62%. So why don't we sacrifice a little bit more alpha so the two numbers are kind of closer to each other. All right, but the beta number has improved significantly. How about I change P to the probability of y being less than or equal to 40. Obviously, we need to find a better way of doing all these things, right? So this is equal to the sum. I'm going to add up the first 40 numbers. There you go. So the alpha, the probability of committing a type, oh wow. Okay, so actually this is a little bit bigger than I expected. How about 35 only? All right, so I think I would prefer 35. Oops. Okay, let's try it again. Start from here all the way up to 35. Do you guys see how I'm struggling to get a good alpha and beta for my hypothesis test, right? So this is good. About roughly 2% of committing an error. I think it's really reasonable. Alpha. Let's see what will be the sacrifice. So probability of type 1 error is 2.23%. I think it is reasonable. Now let's see on the other side. First, the probability that, again, y is less than or equal to 35, given that the true probability is 0.3. So that is equal to the sum of the first 35 numbers. There you go. Close parenthesis, press enter. Now notice the difference between these two. They are not the same numbers, right? Because here it's 0.5. We are using the null hypothesis. Versus in this one, it is 0.3, the true one. The true is 0.3, yeah. Wow, look at that! I love this. So the probability that, as a result, y is strictly greater than 35 is simply equal to 1 minus that number. Aha! Nice! Do you guys see what just happened in here? Wow, so this is a really good result, as you guys can see. So we were able to, we just increased the alpha a little bit, right? But from 0 to 2.23%. But look at the reduction in the type 2 to error, significantly down. At 2% sacrifice on the alpha, we gained a 60% gain on the beta, right? So probability of type 2 okay, let's write it like this. Type 2 error is only 2, which is kind of acceptable, I think, right? So that's it. So we are not favoring one over another. So we have a 2.23% probability of committing a type 1 error, a 2.74% probability of committing a type 2 error, and so this is a reasonable thing. So we were able to get these better results by increasing the sample size. Even a sample size of 90 is way better, right? Versus compare it with a sample size of 15, I should say. The alpha was increased, but and we were able to decrease the beta, but both of them were they looked like as if they were a little bit bigger, right? 15% error is still a pretty big error, versus in this one, a 28% error. These are big errors. So by just increasing the sample size, we were able to reduce both of them. So now the alpha is like 2.23%, and this one is like 2.74, was it? 2.74%. Really, really good. But do you guys see my struggle about choosing the correct rejection region? So this will continue. So what we will do next is we will try to have a bit better feeling about, I mean, we will standardize this. So we will come up with the idea that alpha should be like 5% or 1%. So we will have a look into those. All right. So hope to see you guys in our next lecture.